Chapter 8 Non-Electrolyte Solutions, Section 8.6 The Gibbs-Duhem Equation. The Gibbs-Duhem equation is this: if we have a liquid mixture, we can prove the sum of Ni d mu I is equal to negative S dt plus VdP. Ni and mu I are the number of moles and chemical potential of species I. STVP are the entropy, temperature, volume, and pressure of the entire mixture. We can prove this equation, and then we'll talk about the applications of the Gibbs-Duhem equation. First, let's look at the proof. The Gibbs energy of a liquid mixture is the sum of Ni mu I. This is not obvious. We can prove this starting from the definition of the chemical potential. The chemical potential can be defined by this equation. dG is negative S dt plus VdP plus the sum of mu I dNi. G, S, T, Vp are the Gibbs energy, entropy, temperature, volume, and pressure of the entire liquid mixture. Mu I is the chemical potential of species I, Ni is the number of moles of species I. We can integrate this equation under a specified temperature and pressure. In that case, since dt is 0, dP is also 0, the integral of dG is equal to the integral of the sum of mu I dNi under the given temperature and given pressure condition. On the left hand side, you get delta G. On the right hand side, you have the integral of mu I dNi. And over here, we want to make sure this Ni goes from 0 to the final number of moles of species I. And we want to integrate this with the mole fractions of all components being held constant. In that case, this mu sub I is independent of Ni. This mu sub I is constant. And therefore, we have the integral of dG is equal to this sum of mu I and then the integral of dNi. The integral of dNi is simply Ni in the end. And therefore, we have delta G is equal to mu I Ni. And this delta G is the Gibbs energy of the liquid mixture with N1 moles of species 1, N2 moles of species 2, etc., minus just 0, because our initial state of this integral is just nothing. So we integrate this dNi from nothing to the final number of moles of species I. So therefore, we can prove this. The Gibbs energy of a liquid mixture is the sum of Ni mu I. We can then take the exact differential of G. dG is then the sum of Ni d mu I plus the sum of mu I dNi. We just use the product rule in calculus here. The differential of a product of Ni mu I is simply Ni d mu I plus mu I dNi. Now we have this equation, and also we have this equation as the definition of chemical potential. We compare these two equations, and then we find that this is equal to this, and therefore we cancel the sum of mu I dNi here with this mu I dNi here. These two cancel, and then we have this sum is equal to negative S dt plus VdP. And this is the Gibbs-Duhem equation. The sum of Ni d mu I is equal to negative S dt plus VdP. When there is only one chemical, the Gibbs-Duhem equation is reduced to this: d mu because we have only one chemical here, it's just the N1 d mu 1 is equal to negative S dt plus VdP, right? And since we have only one chemical, we don't need to write the subscript 1. And therefore, we have just d mu is negative S dt plus VdP divided by N. And then we have this equation. D mu is negative molar entropy times dt plus molar volume dP, and this is simply molar Gibbs energy over here. And we have d mu is equal to dgm when we have only one chemical. The chemical potential of a pure chemical is simply its molar Gibbs energy. And we can also reduce this Gibbs-Duhem equation when the temperature is constant and pressure is constant. When temperature and pressure are both constant, dt is 0, dP is 0, therefore the sum of Ni d mu I is 0. So we have this Gibbs-Duhem equation under constant Tp, which is the sum of Ni d mu I is 0. Now let's look at one numerical example problem, 8.6.1. Assume 0.00001 mole helium is added into 1 bar gas mixture of 0.4 mole helium and 0.6 mole argon at room temperature. Numerically verify the Gibbs-Duhem equation. So this is the Duhem equation, but numerically we need to change this differential, the exact differential here, d, to delta. Delta is the finite difference. So we just need to numerically verify this under the constant temperature and pressure condition. After adding the very small amount of helium, the pressure of helium changes from 0.4 to 0.400006 bars. Meanwhile, the pressure of argon drops from 0.6 to 0.599994 bars. Again, it's just because by adding this helium into this system, we increase the mole fraction of helium and decrease the mole fraction of argon. And the total pressure is still 1 bar. Now let's look at this change of the chemical potential of helium and the change of the chemical potential of argon. We will use this equation. Mu is mu naught plus RT times the logarithm of the actual pressure over P naught. So this P naught is the standard state. Now let's look at the change of chemical potential of helium. It's RT times the natural logarithm of the final pressure over initial pressure. Same for argon, so we use these two equations here. We have delta mu of helium versus delta mu of argon. RT and RT cancel, and then we have the logarithm of this for helium on top, logarithm of this ratio for argon on the bottom, and then we get negative 1.49998125. Now let's look at the ratio between the number of moles of argon versus the number of moles of helium. Number of moles of argon is 0.6. The number of helium will take the average between the initial number of moles, 0.4, and the final number of moles, which is 0.40001. And then we take the average. That's why we have this number. The ratio is 1.49998125. Compare this number and this number. They agree with each other to 1, 2, 3, 4, 5, 6, 7, 8. To 8 decimal places. That's very impressive for its numerical accuracy or agreement. And therefore, N helium times delta mu helium is approximately equal to negative N argon times delta mu argon. So you can move this to the left hand side. Therefore, the sum of Ni delta mu I is roughly 0. So we just showed this equation holds numerically, and if we further reduce this number of moles, we approach the exact Gibbs-Duhem equation. The sum of mu I d mu I is exactly 0. For an ideal binary solution, we can verify the Gibbs-Duhem equation similarly by simply replacing the partial pressures of the two components with the mole fractions. Oh, sorry about this typo here. So it does not have to be a solution, it can be a mixture of ideal gases. So we have this Gibbs-Duhem equation, originally derived for ideal solutions, but you can use the same equation for both the gas phase and binary solutions. For any binary solution at constant temperature and pressure, we can use the Gibbs-Duhem equation over here. The sum of Ni d mu I is equal to N1 d mu 1 plus N2 d mu 2, and this is 0 if we have only two components. We can then divide both sides of the above equation by n, where n is N1 plus N2, and then we get this equation: x1 times d mu 1 plus x2 times d mu 2 is always 0. We will now use this equation to discover one application of the Gibbs-Duhem equation. So if species 1 obeys Raoult's law, then we have mu1 in the solution equals mu1 star. That means pure liquid component 1 plus RT times ln x1. And since we have x1 times d mu1 in solution plus x2 d mu2 in the solution equals 0, this is the Gibbs-Duhem equation over here, just a different format. And then we have this equation. We are replacing mu1 in the solution with mu1 star plus RT times the natural logarithm of x1. x1 is a mole fraction of component 1 in the solution, and d mu1 is 0 because d mu1 star is 0 because mu1 star is a constant. Then we have this equation. And because d ln x1 over dx1 is 1 over x1, this is just calculus. Well, it's just because, the differential of ln x is just 1 over x. We can have this equation for x1 as well. And then we have this equation because you can see if we move things around, d ln x1 multiplied by x1 is dx1, so we have this equation. And now dx1 is negative dx2. Why is that? x1 plus x2 equals 1. So x1 is 1 minus x2. So the differential of x1 is negative dx2. So we have this equation. And once we have this equation, we can rearrange this equation. The exact differential of mu2 in a solution is simply RT times dx2 over x2. Now we can integrate both sides, and then we get this equation. The chemical potential of component 2 in a solution is equal to mu2 star plus RT times the natural logarithm of x2. Mu2 star is the chemical potential of pure component 2. x2 is the mole fraction of component 2 in the solution. So again, the chemical potential of component 2 in a solution is lower than mu2 star by this amount. This amount depends on its mole fraction. So here we have one application of this Gibbs-Duhem equation. This is the Gibbs-Duhem equation under constant temperature and pressure condition. This is also Gibbs-Duhem equation because this equation and this equation just differ by a factor of n. So given the Gibbs-Duhem equation, we can actually prove this. If species 1 in the solution obeys Raoult's law, then this component 2 or species 2 also obeys Raoult's law in the same solution. Alright, so this is our final conclusion. In a binary solution, if species 1 obeys Raoult's law, so does species 2. And this is one of the applications of using the Gibbs-Duhem equation.